Abby, I can't hear you. Your microphone is off, I think.
Well, thank you. Yeah, I forgot to press 1, 2. That's the first thing before 1, 5. Okay, thank you. Well, okay, let's start over. Today we'll start a new chapter, which is the existence of test elements and test ideals. Okay. Well, I guess test ideals modules. Okay, so I was saying that this may take us this whole week and a little bit of the next one, perhaps the next one overall. But okay, so let's do this. What is the goal? The goal is to take a Cartier module and to prove that the test module exists. I remember that this is this Cartier submodule of M. It's the smallest Cartier submodule of M that generically agrees with M. Okay. And so we're gonna do this if, so the point is to prove that this exists, and we're gonna do this if somehow it is a rank condition on either one of them. So if the rank of M is 1, so this means that essentially M can be thought of as an ideal of R. Okay, or if the rank, let's say, let's put it like this, is also 1. So in both cases, either means that they are both generally 1 element. That's what I mean at least. Okay. So somehow it's a problem about how many elements generate either M or C. Okay. But this is conjecture to hold in general. Actually, if you restrict yourself to algebras of finite type, you don't need any of these hypotheses. Okay, but we won't do that proof. Because actually, the only cases we care about in this course are these two. Either we're working here with R, and then we study the singularities of the pair, or we put here omega, right? And that's essentially the examples we're going to be playing with. So that's essentially the reason why we will do only these 2 cases. Okay. So we're going to start with the first theorem here. So this theorem tells you a bit about the nature of what we have to prove. This theorem tells you that the existence of test modules is equivalent to the generic F regularity of F pure Cartier modules. Okay, so we're trying to prove this existence, so we need to understand what it means for this thing to exist. So the theorem is as follows. Let's take a Cartier module. This is going to be Cartier module over a base ring R. Okay, so C is a Cartier algebra over R acting on M by P inverse linear maps, or Q inverse linear maps, if you will. So this is the setup. And so then this module exists if and only if the following happens. There exists Let me put it in geometric terms. I think in geometric terms is a little bit better, but then we can do the algebraic translation too. So if there exists an open, and I'm going to take this open of the spectrum of R to be principal. You know, it is going to be D of C. Remember, if you want, this is the spec of R localized at C. You know, this maps inside the spec of R as a principal open. Okay? So there exists a principal open. Remember, these are the keys in the spectrum such that what? C avoids P. C doesn't vanish as a function of P. Right? Or in other words, you can look at the closed subset out by C, and this is the complement, right? So I'm claiming that there is an open in the spectrum of R with the following properties. Let's put it over here. Such that it has two important properties. First of all, VC intersection the support of the M comma C is dense. Well, first of all, this is an open, right? So here I have a subspace, and I intersect it with an open that gives me an open, right? In the induced topology. So the support is closed, and so that gives me an open. So this is dense this is an open dense. The open is for free. What I'm saying here is that it's dense in the support. So the other thing to notice here is that when I write sigma, what I'm saying is that I'm replacing my Cartier module by its representative in the crystal that is pure, F pure. That's it. So more classically, you would see this sort of thing saying, okay, I'm going to see that this is F pure to start with. And then I'll just remove sigma. Okay, so let's just do this. And so what does it mean to be dense? Right? In here. It means essentially that you have to contain all the generic points of that closed subset. Or that C avoids all minimal points of this closed subset, meaning that it avoids the minimal primes of the annihilator of this ideal. Okay? So let me just say, because you often see this written down like this in maybe more algebraic articles, i.e. C, let me just say this, avoids all minimal primes, meaning generic points, right? Generic points of this support. That's the first condition. This open has to be sufficiently large. It has to see sufficiently, or has to see sufficient information of this sigma. So second, and this is the point. So we look at the pair. So here I'm going to look at the pure component of my pair, and I'm going to localize it. Okay, along C. So right, this means taking this whole structure and restricting it to this open subset. Right. So remember, well, this means like I'm gonna localize every single thing, and we have seen that probably was an exercise that sigma commutes with localization, so it is a geometric thing. Okay. I'm going to take this pair, and what I want of this pair is that it is a regular. Okay, So in other words, the test module exists if and only if generically its crystal is a regular. Okay. So when an open neighborhood containing every single minimal prime, my Cartier module is a breaker. Okay. So, and then after this, there's a standard punchline. It's moreover. I should write it smaller. Moreover, where is it? Moreover, the test module can be computed as follows. This thing is, well, let me put it in words, is the Cartier submodule generated by CT times sigma comma C for any t, but different from 0. So in particular, you can take t equals 1. But what I want to, for later, we're gonna need to play with t a little bit. So I'm gonna say that you can use any t you want. Okay. So in other words, let me just put it as an equation because often people write it like this. Once you find that C, you can write down your Cartier module as guess what you can say. It's gonna be, okay, let me write it down like this. C, I'm gonna write C T sigma n comma C plus C plus CT sigma n comma C. Okay. So you often see this equation from the literature. Is okay? It's a long theorem, is that? It's the key to this system thing. So that's going to let us do a whole bunch of reductions. And so, well, the important definition is that C, any such a C, is referred to, let me say, any such a C, which you can see any such a C in R is referred to as a, what did you think? Test element. Of the Cartier module R comma C. Okay. So, but I guess the remark I was about to make is that if n equals R, well, C is an element of the test ideal. And that's why test modules are called test ideals. So you can see the flavor here, right? People were trying to check for something, and they say that you can check something on an open neighborhood, you know, so this is a testing element for something. And then the test ideal is generated by test elements. So that's why the test ideal is called the test ideal, because it's made of the test elements that you can use to check for irregularity and so on. That's the historic reason for the names. So, I don't have any questions with this? Else we can get to the proof. The proof is not very difficult. well, with everything we've done so far, actually it's not so difficult. It's so hard, isn't it? Okay, this is the first trick of proof. The first trick, I think it's the trick Manuel is very proud of, because yeah, all this formulation, crystals and stuff lets you do net reduction. So first of all, remember the test module is an invariant of the crystal. So and let me forget about C. I'm just going to write down sigma n have the same test module, right? Two modules that are nil isomorphic have the same test module. So what this means is that we may assume that n, I guess n comma c, is a pure. And then we may do the standard trick that we have done a couple of times before. Then we can replace R by the annihilator. So the point is that now this is a radical ideal. The annihilator of n, which is radical, and assume two things. First of all, n is supported everywhere. Everywhere. And second, R is reduced. Okay. Pardon? M is supported everywhere. In other words, the support of M is the spectrum of R, and that R is reduced. Standard reduction. But if you remember, this reduction took us a while. Maybe we spent a lecture working out this reduction. This is the fact that, you know, like the category restricts well, you know, across explosive schemes and so on. You remember that part? So yeah, this is a reduction we've done before. So I'm just gonna leave it there. But anyways, most often this is the setup which people care about for the existence of these things. Over here. So okay, let's assume that there exists a test element. Let's get into the nicer right. So assume there is an open neighborhood so such that well, now with this reduction, all we can do is assume that there exists dense. Let me just put here dense, meaning that it contains every minimal prime of R, such that we have that the pair MC, CC is a regular. Right? So we're assuming 1 and 2, and we're going to try to prove the existence of test elements, of test ideals. So let me make a claim. If you have any Cartier submodule, such that this equality becomes, this inclusion becomes equality at every generic point or minimal prime eta, then I claim that C times N, C times M is contained in N. Okay. Then I claim that with this claim we're done. So then we are done proving the existence of test elements of test ideal, because it's right there, right? Who is the test? Who is going to be the test module? Because then the test module is going to become Cm comma C. It's going to be, well, it's going to be Cm plus, if you want C1m plus C2m, or not C. Okay, and so on. Right, so in other words, this is the Cartier module generated by Cm. Okay. Right, this is the smallest submodule that agrees generically with M. And here we see that if we have any other such a thing, the test module is going to be contained in there, right? You have this, but then this is a Cartesian module, so it has to contain C1, Cm, C2, Cm, and so on. Okay? So if we can prove this, then we are done. Because then when we claim that the test module is computed as the smallest Cartesian module containing Cm, is this there? Okay? Is this okay? So the content is here. This is the content really of this direction. Let's see how that works. But it actually relies on an exercise. But I hope you did it. So what's happening? So let's look at what we have. We have a submodule that agrees with them generically. But then our hypothesis is that this pair here is a regular, and C, this open, contains every single minimal prime. So what does it follow from the irregularity here? Irregularity means, remember, that if you have any such object, then that object has to be equal to MC, right? So, as proof of the claim. So, well, the point is that when you look at this inclusion, it has to be an equality as the pair, M comma C is a regular over DC. Right? That's the hypothesis. We have this genetic irregularity, and so if we have this hypothesis, you have to conclude that this is an equality. Okay, they agree on that open subset. So, but what does that mean? What does it mean that N inside M is an equality after you localize? It means that there is a T sufficiently large that kills the quotient. Right? It means that, so you have this exact sequence. 0, what is it, N inside M, and then you have the quotient. What this means is that this quotient vanishes on that principal open, and vanishing on that principal open means that you can find a sufficient large power that kills that, well, because these things are finally generated, right? That's an important step here. A module that vanishes when you localize it at C means that, well, you can kill every single one of these generators by some power of C. And so by collecting a sufficient large power, you can kill the whole module. But let's put that, right? So this relies on Cartier modules being finally generated. And actually, this is one of the reasons why we assume that Cartier modules are finally generated. Otherwise, we have no idea of anything. So you can see that here. So we have this scaling here. Now, let's say for some T is sufficiently large. So everything here, everything so far is kind of trivial. But what's happening? But what do we know about this? First of all, well, the category of Cartier modules is abelian, so this quotient, this co-kernel, is a Cartier module, right? But M is being assumed to be F pure. So this Cartier module, this quotient is pure too. Quotients of pure modules are pure. That's pretty okay, I would say. So what is the conclusion about this annihilator? What is the annihilator of an F pure Cartier module? It is radical, right? There was an observation we had. It's analogous to the fact that, well, yeah, we have used it already, right? But it's analogous to this fact that pure rings are reduced. Okay. So this is radical. That's the magic there. Then, it follows, then C Mn is 0. Right? C to the T belongs to the annihilator. Then C has to belong to the annihilator of that quotient. And well, this is just a fancy way or another way to say that Cm is containing M. Okay. Just basic algebra, you know? But you see, this is the exercise I was telling you that we rely on. But at this point, we have used it many times already. So I guess it's not surprising. Okay. So let's work on the converse. So we proved that if you have kinetic irregularity, the test ideal exists. Let's prove the other direction. Any questions so far? So conversely, suppose that this exists. Then let's look at the following ideal. Well, let's take M, and then we can take these portions. And then let's take any later. Let's look at all the things killing this. What do we know about it? So let's take, so the point is that this annihilator cannot be inside every minimal prime, right? Because these two things agree generally. So then literally just take any C, let's call this ideal. Okay, let's take any C in I, avoiding every minimal prime. Which exists. So, so I guess the way to put it, yeah, this avoids every minimal prime. So here I just took C such that the first condition we want to prove holds. When you look at the principal open defined by C, you will see every single minimal prime in there. Okay. But the second condition was that when I localize at C, then I get the regularity. But that also follows because then well, technically speaking, this inclusion here is trivial, right? And it's inside there. But I claim that when I do that localization, well, it's just trivial, right? I just choose an element that kills the possible difference, right? So this inclusion, which is trivial because n contains that, now becomes an equality. Okay, but this is the, now you conclude by the fact that the test module commutes with localization, which I think was an exercise at some point too. I hope you remember that. So in general, test modules commute with localization. So you have C. And so you see, that's what it means to be a regular. MC equals its test module. So M is a regular. Well, MC is a regular. Or let's say N comma C localized at C is a regular. Okay. So I told you guys it's a simple proof, but it has certain subtle details that hopefully we already worked on them in previous lectures or exercises. Yeah, so also there is something about this formalism of Cartier modules that somehow lets you write everything down very, very nicely. That's part of it too. So, any questions with this? Perhaps in Zoom? No? Very good. Maybe I need to know this. So this is gonna let us do a massive simplification on the existence of test modules. Because notice what this is saying, right? Like you can always shrink your space as much as you want. Well, not as much as you want. You always keep, when you shrink, you need to keep on. You can shrink on desk opens and prove what the existence there. It's a generic phenomenon, essentially, at this point. Right? And because you can do that, you're going to have the following massive simplification. Existence. So let's put this in a remark. I don't know what's so thirsty today. So then, to show that tau exists, we may shrink if needed to sufficiently, let's say sufficiently small, dense open subsets. So let's say the principle, so that we can always work in different algebraic contexts. That's not necessary, but then you will need more of the language schemes and so on to do so. Okay, so well, the other assumption we've noticed is that this on top, right, on top of assuming n comma c is a pure and the annihilator of n to be 0, right? In particular, r is reduced. So we can trick around, and what does that mean? In particular, so generically, R is regular, right? Because it is reduced. It is R0, right? So that means that there is an open neighborhood, a dense principal open neighborhood, over which R is regular, right? Because it is reduced, it is R0. It is generically regular. So in particular, we may assume that R is regular always think enough so that we avoid all singularities. Right? Or take the Jacobian ideal, take an element of the Jacobian ideal and just forget about it. And what about n? What can we assume about n? N is a finite generic module. And it's going to be generically free because R is reduced, right? When you look at every single point, you're going to get a field, right? There are no embedded primes. So essentially, what R being reduced means is that its total of fractions is a product of fields, right? So generically speaking, M is going to be free. So we may assume that N is free by a certain generic freeness, because it is finite generated, right? So think of R being a domain. Actually, we can assume that R is a regular domain. As well. And so we may assume that M is just free too, and M is free. So because it is regular, it is normal, and so in that particular case, the irreducible components don't intersect. So you have disconnected components. So you can do this massive reduction thanks to this. Okay, so it suffices to prove the existence of test modules over regular domains and for free modules. Okay. This is all good, but this doesn't impose any restriction on C, right? C is still really arbitrary. That's an issue. So the next thing we're going to do is to prove that C essentially can be taken to be finally generated. And that's the next key reduction of this existence. To prove that C can be taken to be finally generated. Any questions so far? So next reduction, we may assume that C is finally generated. For this, we're going to need two lemmas. What are my lemmas? The first lemma is the following. Here. First lemma. So as before, we take a Cartier module. Module over R and a finite ring. So then, what I claim is that there exists a Cartier subalgebra that has two properties. First of all, it is finally generated.
Harry, could you move the camera, please?
Yes. Sorry. Okay. I was thinking to write them over there, actually, in that little square. Sorry about that. So let's go over it again. Let's go over it one more time. So we have a Cartier module initial setup. And so what I claim is that C contains a Cartier subalgebra that is going to be finally generated. So essentially, I'm just going to be taking finally many elements here. I'm just going to take the algebra generated by that. So such that two things happen. First of all, the sigma is the same. So if I take this equals this. Of course, this is an equality, an inclusion, but what I claim is that it becomes an equality. And moreover, if tau exists for n with respect to C prime, then so does tau n comma C n one has right down over here. So tau of n comma C prime is contained in tau n. Maybe I didn't write this in the best way possible, but so there will be a second finally generated Cartier algebra C double prime. So I think the point is this. So first of all, you say that sigma can be computed by finally many elements of C. And then the existence of both, well, the existence with respect to C prime implies this one. But moreover, the test ideal of M with respect to C can be computed by this Cartier algebra C double prime. So here where we have something like this. And so this one here is finally generated as well. Okay. Maybe I should have written it down as two lemmas in one. Well, as two separate lemmas. But yeah, the point is that every single invariant, well, sigma and tau, can be computed with respect to finally generated Cartier subalgebras. Okay. So to prove this one, for example, then I'm going to use this one here. But actually the point is that I could have used this one. I'm going to compute it like this one. So let's see how this works. So let's prove this. Too many proofs today. Sometimes it's too many definitions, sometimes too many proofs. To be more balanced. Okay. So proof. So by replacing, as usual, n with sigma, and comma C, we may assume that N comma C is a pure. So that's the first reduction that we have done many times already, so everything is fine. And so what is the point? So then we have that when we look at this, right? How do you write this down? So you take this huge sum over E non-zero, of all the possible actions. In here we could write kappa of kappa on N, right? That's a gigantic sum, but it lives inside M, right? And so the point is that we can assume that this is an equality. But N is finally generated. It's an Euclidean object. So we can write down this as a finite sum. So then, let me just write it down like this. Then what we have is a sum from I equals 1 to K of kappa I N equals M, right? And so here we're going to have that kappa I belongs to C EI, where the EI is, it's just a set of them, and then all of them different from 0. Okay? So we have this gigantic sum of submodules, and since M is finally generated, that sum is realized by finally many of them. Right? How does that work? M is finally generated again, so it suffices to see where the generators of M live in this sum, and that would be enough. Okay? So let's move over here. So take C prime to be, well, how can I denote it? Like, maybe this is bad notation, but I hope it's understandable. You take the algebra generated by this kappa k things inside here. So you take all the sub-algebras of C that contain those and take intersection, that's like a case of algebra, and it's this. Okay. So that's finally generated, okay? And so you see the first statement that the sigmas agree because, first of all, we just check that this is M. So the sigma is the same. Sigma. So we've got the exact same sigmas for both of them, which is M. So suppose that this thing exists. Why does this imply that this exists? what have we learned today? That the existence is a phenomena about generic F-regularity. So if this exists, it means that n is generically regular with respect to C prime. But if it is irregular with respect to C prime, it is irregular with respect to C. Because any Cartesian module with respect to C prime is a Cartesian module with respect to C. Sorry, the other way around. Any Cartesian module with respect to C is a Cartesian module with respect to C prime. So you have that. Because we have understood what it means for this to exist. It's a generic term of irregularity. So by the previous theorem. Okay? So okay, so we have done the first part. Now let's do the part in which we prove that the test module can be computed by that in case it exists, right? I think the logic is like, okay, if this exists, then this one exists, and moreover, it can be computed by the test module with respect to a finally generated algebra. So, and so how does that work? Well, it exists, and by the theorem, we know how to compute it. T and C I guess you can say it's equal to C applied to Cm. Right? Here I'm saying that the test module is the Cartesian module generated by Cm. So you take this module and you just apply this algebra to it, and you get a cell module out of it, right? So for a test element, over here. Now what? We apply the same trick to tau. Right? This is also finally generated. So it's going to be finally generated, right? It's a submodule of a finally generated module. It's finally generated. So choose generators, right? And they would be hit by something in this sum, right? This sum is gigantic, right? But it's not going to be. It can be taken to be finite, right? So that's the point. So since tau n comma c is finally generated, then we can write tau n comma c. So here we need some good notation. So I guess from r equals 1. Before we use k, then we can use l now. And well, we use kappas. Let's use kappa prime perhaps. Cm for some, I guess kappa I prime that belongs to C, the phi I prime. And so here, now we're going to have certain E primes L in N. And they can be zero. That's all. Okay. So I just took this gigantic sum and I claim that there are finally many sums that realize the equality. Just because this is finally correct. Okay. There isn't much going into it. It's this rather simple argument. And so take C double prime to be C prime adjoin these new elements. Okay. So then, yeah, I think then yeah, we're good. So that's it. We did one more lemma. I guess there is a good reason why people usually skip this proof. Too many lemmas and stuff. But it's not so bad, I think. Okay, one more reduction, or one more lemma. We're almost there. So, lemma. Uh, 300. So, one sec. Very confused about something. Second, I'm really thinking if we need this or we can skip it. I'm slightly confused. I'm missing something. Hmm. Hmm. So let me think about the logic here. So, So I think, okay, the next lemma should tell us that actually the test ideal of n with respect to C prime is a test ideal of n with respect to C double prime. Okay, yeah. Okay, let's do that. So the following lemma is this. So suppose that you have Cartier algebras over R. And so suppose that M is a Cartier C module such that tau M comma C prime is a pure, sorry, such that n comma C prime is a pure. So as we just said before, the sigma of this curve is contained inside the sigma of n comma C. So let me do this in yellow, just real quick. So in general, the sigma is inside the sigma MCPC. Right? That's pretty simple. This is the stable element of the direction of C prime. This is the stable of the direction of C. So it's just going to be inside that. The C prime is inside C. So if this is a pure, they will say here. Well, let me just see. Then so is. That's fine. Then so is n comma C. Okay. That's the part I think about. I'm confusing myself about this because we just did this. So I just explained why it was. If this exists, then so does tau n comma C. We just did that, right? Because we understand what it means. This means that generically speaking, this is a regular. And so then generically speaking, this one's going to be a regular. Okay? So yeah, there is no issue here. Actually, there's an inclusion that is for free, and the other one can be checked generically, and both mean the same thing. So does this one. But what is the content of the lemma is the following, I think. So I'm going to go to the other side. Okay, so at least for grammar. So, sec. I think the part we should care about is moreover, if C is finally generated over C prime, so meaning that you attach a few elements, a prime, something like this, then tau of n comma C prime is computed by tau of n comma C. Okay? So before getting into the proof, which at this point I think it's tricky, but I don't know if I want to leave it as an exercise, but at least I want to write down this conclusion. So proposition, before we get into the proof, or if I decide to leave it as an exercise, proposition, this is the reduction. So I just wanted to write down. Let's see if you are with me. So the existence of test modules follows once we show that for a regular domain, or let me put the conditions here. Regular domain R first, finally generated Cartier algebra over R. Okay. Third, and free. So let's say R free is free as an R module. R free Cartier C module M. Okay. So under this hypothesis, we have to prove that if MC is a pure then MC, CC is irregular for some C different from 0. But now there's only one minimum time. I is a regular domain. So are you guys, do you guys agree with this? So, so to prove the existence, let's think about the proof. It's just about putting everything together. Okay, let me move it a little bit. So you guys can help me here. So what is the proof? We want to prove the existence of test modules. We have seen that we can reduce to the case where R is a domain and R is a free Cartier module. And to prove that, we can also assume that, well, we can assume that it is a pure. And in that case, what we have to prove is generic F regularity. But what we were missing is exactly how you restrict to a finally Cartier algebra. Yeah, from the previous lemma. So what is confusing me is why we need both lemmas. Why the first one is not enough? Do you guys see my confusion? why is this other lemma not? So the first lemma tells us, right, that if we have this Cartier algebra acting on M, the test module is computed by a finally generated one. We replace C prime. So what we can do is replace C prime. We have C prime if purity is preserved with respect to finally generated one. And then the test module, because of the first lemma, is computed by a finally generated one. I don't see why this second lemma is necessary. I mean, it's true, but is it necessary? I don't know if I'm missing a piece of logic here. So in general, this is what you have to prove. You have to prove that if you have a pure pair, then it becomes a regular after localizing. That's what existence means. But what we've been arguing is like you can do that and in a more restricted setup. The fact that you can take a regular domain, that's fine. You just shrink until you avoid all singularities. And you can shrink enough to make M to be free. But then, so you have to argue that you can assume that your algebra is finally generated, but I think the first lemma is enough for that. Because it says that the Cartier, the test ideal is computed by a finally generated one. The second lemma tells you that the test ideal of C prime and the test ideal of C double prime are the same. But I see, but it is only if you have proved the existence for the test module for C prime. If you but still. Do you guys see my confusion or is okay, I think we're totally over time, definitely. So then I think about it, and if I see some problem with the logic that actually requires the second lemma, then I'm gonna bring it up next time. And if it is necessary, then we prove that lemma. But otherwise, we won't get into proving it because it's at least so far it doesn't feel like it's necessary. And so on Thursday, we are gonna prove that under these three conditions. Okay? Sorry.